looked at the energy balance for radiation exchange in gray surfaces. So, we said that the net radiation exchange, if we have an enclosure with n objects with n surfaces and each of them are exchanging radiation with each other, then we said that the net radiation exchange is given by sum over all AI Fij j going from 1 to n, and that is also equal to Ebi minus Ji by 1 minus epsilon I by Ai epsilon. Okay. So, we identified that 1 minus epsilon I by Ai epsilon I is the resistance offered by the surface because of its surface properties for radiation exchange from that surface. Okay. So, now in a similar way we could also identify resistances for radiation exchange between different surfaces. Okay. So, note that this is the resistance for radiation from the surface I, and we can identify resistances for radiation exchange between surfaces. Okay. Between surfaces. Okay. So, radiation exchange between surface I and surface j is given by is Ai Fij into Ji minus j. Okay. So, now we can rewrite this as Ji divided by 1 by Ai Fij. So, if the driving force for radiation exchange is the difference between the corresponding total emission from each of these surfaces, so that is the driving force. Driving force divided by the resistance. Okay. So, one could identify that the resistance that is offered for radiation exchange between surface I and j would be 1 by Ai Fij. Okay. So, this resistance is nothing but 1 by Ai. So, note that this resistance is the resistance offered because of orientation. This is the geometric resistance that is offered by the system because of the orientation of different surfaces. Okay. So, therefore, one could write a resistance network J 1 by Ai Fij. Okay. So, that is the resistance which is offered for radiation exchange between surface I and surface j, whose total emission are Ji and Jj. Okay. So, now based on these two resistances, we can now construct the resistance network for the whole system. Okay. So, supposing Ebi, okay, is the black body radiation for surface I, and Ji is the corresponding total emission from that surface, then the resistance offered is 1 minus epsilon I by Ai epsilon. Okay. Now, this is exchanging radiation with all other surfaces, therefore, you have resistance for which are occurring in parallel, because it is simultaneously exchanging radiation with all other surfaces, therefore, you have resistances which is appearing in parallel. So, this is 1, J1, J2, etc. up to Jn, and these resistances are 1 by Ai Fi1, 1 by Ai Fi2, and this will be 1 by Ai Fi3, and this will be 1 by Ai Fin. Okay. So, that is the resistance network for radiation exchange of surface I with all other surfaces in an enclosure. Okay. So, one could similarly write the radiation exchange for all the other surfaces, right. One could similarly write radiation exchange network for all the other surfaces going from 1 to n. So, in principle, from every node you will have n resistances which are actually coming out of every node. So, how many resistances are there? Total number of resistances for this system. Total number of resistances. What's the total number of resistances? So, every entity you have n of them. Okay. So, that gives you n square, but you have the resistance that is offered by the properties of the surface, right. So, you have one resistance for every surface. So, the total number of resistances is equal to n square plus n. Okay. So, this n square is the resistance offered because of orientation. Resistances due to geometric positions or geometric factor. So, these n square resistances are because of the geometric factors, and obviously they are symmetric, right. And n resistances are because of the resistances due to surface properties. Due to surface properties. What is the resistance offered by the surface? Due to its own surface properties. So, the total number of resistances are n square plus n. Okay. Alright. So, where do we use all this? So, the question is, where do we use all this information? Okay. So, there are two kinds of questions one could typically ask. Okay. So, question 1 is, suppose I know all the temperatures, suppose all surface temperatures are known, okay. Can I estimate, can the radiation okay. So, that is the first class of questions you can answer with some of the things that we have derived so far. Okay. The second class of questions you can answer is, suppose I know the fluxes, suppose I know Qi, okay, I know the net radiation exchange from every surface. Now, that is possible to measure, because if you know how much heat you are supplying or removing in order to maintain an isothermal condition, and that is what will give you what Q net I is, then given that, what is the temperature? You can answer different kinds of questions. Not just that, you can also say what are the individual total emission. So, that question also can be answered. Okay. So, let us look at the first question, how to answer the first question. So, with whatever framework that we have developed so far, so we are going to use what is called the Oppenheim matrix method to answer question 1 and question 2. Okay. Now it's nothing but just transforming all the energy balances that we have written so far in a matrix vector form, so that it looks elegant to solve the problem and looks easy to solve the problem. Okay. So suppose I know all the surface temperatures, I want to find out what is the total emission from every surface, right? Net emission from every surface. Now if I know that, I am done. I can find out the net heat transfer rate. So we have the energy balance. So EBI minus JI divided by 1 minus epsilon I, AI epsilon I, that's equal to Q net I equal to JI 1 by summation over J. Okay. So this is the emission from the surface with respect to its own properties, and this is the radiation exchange between that surface and all the other surfaces in the enclosure. Okay. So supposing I know the temperatures, which quantity in this expression is a known quantity? Suppose I know all the temperatures. Suppose I know the temperature of all the surfaces and I maintain under isothermal conditions. So which quantity is a known quantity here? What are the quantities which are known here? Do I know epsilon I? So if I say the properties are known, then I know epsilon I. Epsilon I is a known quantity, okay, and I can find out what the area of the surface is, total area of the surface. What else do I know? What else do I know? If I know the temperatures, what else do I know? I know EBI. EBI is just the black body radiation at that temperature, right? So this means EBI equal to sigma Ti to the power of 4 is a known quantity, right? So what do we need to estimate? We need to find out all the JIs. We need to find out the total emission from every surface given these quantities. Is it a solvable problem? How many equations are there? How many? N equations. So you have one equation for every value of I, right? So this equation is valid for all I going from 1 to N. Okay. Is it a linear or a non-linear problem? It's linear in J, so we should be able to find the solution. So the way to represent this is, so EBI divided by 1 minus epsilon I by AI epsilon I, that's equal to sum J equal to 1 to N JI divided by 1 by AI Fij plus Ji by 1 minus epsilon I epsilon. Okay. So now I can write this in the matrix vector form. So note that this is for all I going from 1 to N. So now I can write this as a matrix vector problem. So that's EB1 by 1 minus epsilon 1 by A1 epsilon 1 An epsilon n, and that's equal to, we have a matrix multiplied by J1 all the way up to Jn. What's the first element in the matrix? That's only for the first term. That's summed over all 1 to n, right. So similarly, you have a summation here, j going from 1 to n. Okay. So I'll open up and write it out, write all the terms separately in a minute, but you should understand the structure of this matrix. Okay. So let's just quickly so if I call this matrix as A, okay, so if I call this matrix as A matrix, and if I call this as J vector, and if I call this as B vector, okay, so the total emission from all the surfaces is just the solution of this matrix problem, right. So J will be A inverse times B, okay. So where if I open up the A matrix A11, the first element in the matrix will be sum over all j 1 by A1 F1j inverse plus 1 by 1 minus epsilon 1 divided by A1 epsilon 1, okay. So that will be the first term. So if I now want to find out what is the general diagonal term, so Aii will simply be, I replace 1 with I, okay. So that is the general diagonal term, and then if I look at the off diagonal terms, A12 will be 1 by minus 1 by A1 F12 inverse, right. So if I replace, if I want to find the general non-diagonal term, so Aij will be A1 F1j, okay, and then I replace the first index with I, Ai Fij, okay. So that is it. So it is so easy to find out what this matrix is. Aii is sum over j equal to 1 to n, 1 by Ai Fii inverse, Fij inverse, excuse me, plus 1 by 1 minus epsilon I divided by Ai epsilon I, and the off diagonal terms are Aij is minus 1 by Ai Fij inverse. Yes, it is, because of the reciprocity relationship. It is symmetric, and it has to be symmetric, because if surface 1 is exchanging with surface 2, surface 2 is in turn exchanging with 1. So it has to be symmetric. So we can find out the total emission simply by solving this matrix problem, and so J will be A inverse times B, okay. So this is if all the temperatures are known. Okay, what if all the fluxes are known or the rate, heat transport rate is known? So this is the first problem. What about the second one, where if temperatures are not known, but we know how to estimate the QIs? How do we solve this problem? Can we still use the same framework? No, Qi minus Ji. That is right. So that is the expression. We don't know, so we are going to find out Ji. We are going to find Ji. So we know Q net, we are going to find Ji. Now if you know Ji, you know Ebi from this expression. So there are three terms here. There is a first term, there is a second term, and there is a third term, right? So there are three terms here. Now what I can do is I can equate first and the third. So use the first and third. So use 1 and 3, term 1 and 3, and find Ji. Find Ji, okay, find all the total emissivities. Then use 1 and 2 and find Ebi. Okay, so you can find EBI. So once you know EBI, from here you can find temperatures. That's it. So algorithm is very simple. It's still the same framework, except that these elements inside the matrix is going to be different. So that's going to be Q1 and Qn, and the diagonal elements will not have this summation term, will not have this additional term here. So that will be, so this will be sum j equal to 1 to n 1 by a to f2j inverse, etc., and you just complete the matrix. Okay, so this will give you, again it's A and this is B vector. So solving this matrix vector problem will actually give you the total emission from all the surfaces if Q net I is known, and then equating 1 and 2, you will be able to find the EBI for every surface, and from that you can find out the temperatures. Okay, so if we just, so this is for problem 2, where all QIs are known. The elements will simply be, the diagonal elements will be summation of all the view factors, and the off diagonal terms will remain the same. Okay, so this is for the second class of problem, where you can still use the same Oppenheim matrix method, except that you will have to equate different terms in your energy balance.